particular temperature. Alright? Okay, any question? Anything that you need to clarify at this point? No? Okay, then let's move on. Okay, so the concentrations of these substances are excluded from equilibrium expression. Now, I want you to think a little bit about this to understand why this is so. The concentration of a solid is proportional to the density. So, increasing the concentration of a solid is basically means increasing the density of a solid. Do you think that you can do that easily? I want you to really think about it. How can you increase the density of a solid? Nicholas, go, you're already thinking. So, cannot. It may be possible, but it would require you to do things like subjecting it to extremely high pressure. For example, like in a black hole or something like that. Okay? When you do the science, I want you to start thinking about stuff. Because Cambridge is actually getting very creative in your exam questions. And if you all don't start thinking about it or getting used to it, you are going to have trouble. Okay, never mind, there are more questions to follow. So the next time, Nicholas Goh will get to name someone he would like to answer the question. So anyone that Nicholas Goh cannot touch Chow. Chow is my chemistry rep, so it's immune. Okay, the other thing that we want to talk about is where it is the solvent. For example, water. The usual example that we come across is water, and where is a problem. Now, I want you to look at that statement in red. Water, the concentration of water. The first time as a student, I came across this concept, I found it mind-blowing. It's like, what? Water got concentration? It turns out that yes, water does have the concentration. If you go and calculate it out, there is a certain amount of water in a fixed volume. So therefore, yeah, it has a concentration. And if you work it out, it's actually about 55.6 mole per dm cube. There is an actual number there. Okay? Now, some equilibrium constants do not include the concentration of water, but the problem is some do, and we'll touch on that. Okay, so for example, you have this water reacting with the carbonate, and you get OH minus and hydrogen carbonate. An easy way of thinking of this is sodium carbonate dissolving in water. And this reaction actually is called hydrolysis. Okay, so if you go and put damp red litmus paper in sodium carbonate solution, you will find that it's not neutral. It's actually alkaline. Okay, it will turn blue. Okay, so in this case, water as a reactant is also the solvent. but the concentration of water is very large compared to that of the carbonate, the OH minus and the hydrogen carbonate. So we don't actually go and put it in the Kc expression. Okay, if you want to actual numbers, normally you make a carbonate solution is going to be less than 1 mole per dm cube. Okay, the concentration of OH minus is going to be like maybe 10 to the power minus 3 or something like that. Okay, hydrogen carbonate about the same. So water is 55.5, 55.6, so it's much larger and it's going to be constant. So at least constant to 3 etc. Okay? So that's why they do it. Now, however, there are instances where you need to include the concentration of water in the Kc expression. There is one example in the past 10 years, I think, or maybe 15 years, where Cambridge actually gave the students the concentration of water. Now, if they do that, and they don't normally do it, you must ask yourself, why did they do it? Okay? Because in that case, when they did it, they wanted the students to include the concentration of water in the question. I mean, in their answer. Okay, so you have to be alert for stuff like this. Okay, so reaction between ethanoic acid and ethanol. Okay, this is an organic reaction. You are trying to make an ester. Okay, water is a product. So the question I want you to ask, what's the solvent? Okay, and is there likely to be a large amount of water? So the Kc expression actually here, you would include the concentration of water, because if it's an organic reaction, the solvent is not likely to be water, because the other substances may not dissolve well in it. In this case, okay, the ethanoic acid, the ethanol will dissolve in water, but the ester, ethyl ethanoate, will not dissolve well. Okay? So here water must be included in this equilibrium expression because it's not a solvent. The amount of water produced will change the concentration of water significantly. Alright? And now you're very excited about ethyl ethanoate. Okay, you all my classes are in for a bad time because for most of term 3, I'm the lecturer. E, not to worry, I know some of you. I also start calling your names. Okay. Now, experimental determination of Kc. I want you all to pay attention to this because we are going to look at why we do certain things. And increasingly, this is the focus of exam questions. Okay? So look at there, Mr. Tan has highlighted 3 questions that he put it in bold. Now, mix a known amount of reactants in a conical flask. Okay? Reaction mixture is allowed to equilibrate in a thermostated water bath. That means a temperature controlled water bath. Okay, an easy way for you to indicate this is to go and stick a thermometer in there and draw it in if you are asked to draw a diagram. Okay, A 10 cm cube of mixture is run into a flask containing ice and water. I want you to think about why did they put ice and water inside there. Okay, next, the ethanoic acid is rapidly titrated, okay, with an alkali, example sodium hydroxide. So think about why it's rapidly done. Okay, so think about why you need to control the temperature at first in the water bath. Why, when you extract the sample, do you need to put it in ice? And third, why do you need to do the titration rapidly? Okay? So, why is there a need to let the equilibrium establish at a particular temperature by making use of a temperature control water bath? This one is quite easy to explain. You know that Kc is affected by temperature. So you don't want any fluctuations in temperature to change the equilibrium position. Okay, and we therefore result in changes to the equilibrium constant. Okay? If you haven't finished, put up your hand. No. Okay. Done? Okay, let's look at, before we go on to the next point that we discussed, the next point is actually linked to kinetics. In order for the concentration to change, something must happen. And that something must happen in the time in which it needs to happen needs to be short enough for it to be significant. I can tell you, for example, this roof is going to collapse. But if it takes 10,000 years, then we are not particularly bothered about that, right? So I want you to think, what does the ice do? And how does that affect? What does that affect? Okay? Now, basically, the ice, whenever you want things to stop, or you don't want things to happen, you want to slow down the reaction. So you change the temperature, you lower the temperature. Okay? So, at that lower temperature, the rate of the forward and the backward reactions are slowed down. Okay? So, therefore, the shift in equilibrium position is basically going to be very slow. Alright? Got to slow the reactions down. Okay. Now, why do you need to titrate with the sodium hydroxide rapidly? Think about what does the sodium hydroxide do and what effect it can have on the equilibrium. Okay? So, when you titrate with sodium hydroxide, you are trying to determine the amount of the ethanoic acid. Okay? But when you remove the ethanoic acid, you change the equilibrium. Okay? The equilibrium is disturbed. The concentration of the ethanoic acid should decrease. The position of equilibrium should shift to the left. That means the ester, the CH3, COO, CH2, CH3 will start to react with the water, and then it will become ethanoic acid and ethanol. Alright? We are done with this one? Okay. Okay? Done? Okay, so position equilibrium will shift to the left to produce more acid. Rapid titration ensures that this is prevented as much as possible. Now, in case any of you are interested in this, the reaction of the sodium hydroxide and the ethanoic acid is extremely rapid. So even though the lower temperature should slow down the rate, it doesn't, it's still, the reaction is so fast that it doesn't matter very much. Okay, because it's practically instantaneous. Okay? Alright? Okay. So, quick summary. Equilibrium constant, that's how you express the equilibrium constant. A, B, C, and D should not be solids or solvents. Okay, Kc is a constant at constant temperature. Right? Okay, now we go on to something called the Kp. This applies for gases only. So, it is similar to Kc. Now, so for the equilibrium constant, you will get Kp equals to the partial pressure of the products over the partial pressure of the reactants raised to the the constant in the stoichiometric equation. Okay? Now, the partial pressure is proportional to concentration, as you know from your gases lecture. Okay? And so basically it's for gases, and instead of using concentrations, you use partial pressure. Because for gases, often measuring the partial pressure is easier than measuring the concentration. Okay, so this is basically a recap. If you have a mixture of gases that are not reacting, the partial pressure of, let's say, A is the same as the pressure it would have if it was alone and occupying the same volume under the same conditions. Okay? So, the total pressure is going to be equal to the sum of the partial pressures. This also was in the gases tutorial, gases lecture, which you already know. Okay, so now this part is the one that I think is important to emphasize. The partial pressure of a gas A is the mole fraction of gas A multiplied by the total pressure, where the mole fraction is the amount of A over the total amount. Is that written there for you? Yes. Okay? Okay, units of Kp similar to that of Kc. There's no fixed units. It's dependent on how you write the equilibrium expression. The units usually are expressed in terms of atmosphere, Pascal, or Newton per meter squared. For non-physics students, Pascal and Newton per meter squared are actually the same thing. Okay? Alright? Okay. Again, Kp is a constant at constant temperature. Okay, you are going to learn a lot of constants, and the ones with big K, you will learn Kp, Kc, later on I will teach you Ka, Kb, there will be a Ksp. All these big Ks, they are fundamental, they are important constants, and they will be usually only affected by temperature. They are not affected by changes in concentration, they are not affected by changes in pressure. Okay? Okay, so what else do we have to say? Kp, because it's for gases only, you disregard solids and liquids from the equilibrium constant, equilibrium expression, as they contribute little to pressure. Now, having said that, I want to say a little warning here. If you look at the equation and then you see that there is a liquid present, you must think twice. Are you supposed to write a case Kp or not? Because if that's the case, you think you are supposed to write a Kc. Unless the exam question specifically tells you write Kp. Okay? I issue these warnings because Cambridge is getting increasingly creative. Oops, I forgot I'm on video. I should not say these things. Okay, never mind. I think it's not that intimidating. Okay. Kc, Kp, constant only at constant temperature, changes only. Okay. This is what I just said is unaffected by changes in concentration of partial pressure. Okay, here, this is important because you need to think about it. Catalyst simply makes the reactions faster. It will make forward reaction faster, it will make backward reaction faster. However, it doesn't change the position of equilibrium. Okay? That is something for you to remember. The catalyst doesn't allow you to produce more of a product. It simply allows you to produce the product faster. Okay. Magnitude of equilibrium constant indicates the extent of a chemical reaction. Okay, this one is something useful for you to think about. Look at the number. Let's say I tell you the Kc is 100. Okay? Are you going to have more of C and D? Or are you going to have more of A and D? More of the C and D, right? Okay? If it's smaller than 1, you should have more than the A and D. So it's something for you. Sometimes when you look at a question, you look at a number, they may ask you, what does it mean when you have a particular value? If I have a Kc and it's like 10 million, then it can probably tell you that the reaction is essentially one way. Almost all of it will form the products. Right? Okay, so large value of Kc is a high proportion of products compared to the reactant. Equilibrium position lies to the right. Small value of Kc, only a small fraction of reactants has been converted to products. Okay? It might be another way sometimes I think of Kc is actually like a ratio of the products to the reactants. So high ratio means you have more of the products. Alright? Okay, so position equilibrium lies to the left. Now, equilibrium constant gives no information of the time taken to establish the chemical equilibrium. How long it takes depends not on the Kc, but of the rate equation. Okay? It depends on the rate. Okay, so go and do this checkpoint 2. Do checkpoint 2, checkpoint 3. Mostly done. Show you the answers. Okay, these first two I think what I want you to take note of, if you are given the reverse of a reaction, right, the backward reaction, then the Kc is simply the reciprocal. It's probably good to remember for MCQ. Okay? So, N2O4 to NO2, you get KCA. A is just a random number constant that we take. Okay? Then if you write the other way around, NO2 to N2O4, the Kc will be 1 over A. Okay. Then, here, you have 2 NO2 to 4 NO2. Now, in these cases, don't go and cancel anything to simplify it. Okay, you just follow the expression and you should get A squared. Okay? Then you have, okay, that is this. Have you all copied now? Can I move to the next part? Done? Okay. Okay. Now, I want you to take note of those comments there, which is important. The Kc is dependent on the equation that you write. Therefore, whenever you quote a Kc, it must have an equation with it. If not, it doesn't mean much. Alright? Okay, so this one, the next one is interesting because there are solids there, so you just ignore them and then it's just for concentration of the gas. Okay, here the units cancel off. Here you don't include water. Okay? Alright? Any topic? Okay, so the Kp expression, I asked whether you all finish copying and then you all just keep quiet and then I hear a wow. Just put up your hand now. Are we done? No? No one finish? Okay, next one. Okay, I need to finish with this. I go back a slide because some people are asking something. A. I want you to listen to this carefully. I wasn't one of the most hardworking students in school, but I listened very carefully to the teachers. That's how I get away doing less work. Now, this thing, some people are asking, why do I include water? And this one, why I excluded water? I thought I explained that at length just now. This is an organic reaction. The solvent is not water. Okay? So they leave it out. The second reaction is the solvent is water. Sorry, the first one, the solvent is not water, so they include it. The second one, the solvent is water, so they exclude it. So it is explained in detail on page. Hang on, Which page? Page 6. The last bullet point under equilibrium constant. Okay? So you're going to look at that. Okay. Now, can do checkpoint 3? Have you done? Tell me, have you done 3? Nicholas Wong have done already now. Then why are you looking up and not looking at your paper? What you can notice about reaction 1 and 2 is that reaction 2 is reaction 1 reverse and half. I'm done. Yes, right. So find that you have less friends than you. Try to solve it. Okay, can do this. It's 1 over Kc because it's the reverse reaction, and it's half because they divided everything in reaction 1 by 2. Okay? So that's why it's to the power of half. Alright? Okay, let's go to the next one. Answer B. Okay, so the next section, we need to talk about how do you know when equilibrium has been achieved. Okay? So you are going to get this, it's a new, it's not a new expression, but it's a new a different way of thinking of it, reaction quotient Q. Now, I want you to think about this for a couple of moments. You can actually, let's say you have a reaction and it's progressing, right? So, when you can actually measure the concentrations at any point in time. Okay? So, if you measure the amount, let's say products formed and the amount of reactants formed, to those, then you calculate into the Kc expression, you get a number. Does that number tell you anything? Can you predict anything for that number? Okay? Essentially, this is what we are trying to do with the QC, the reaction quotient. You are putting it in the same expression as the Kc, and you are trying to compare it with the Kc value and see what prediction you can make. Okay, so concentrations are the same. Okay, the way you calculate this is the same as for Kc. Now, I need you to pay attention to this because this is really new to you. When the easiest situation is when QC is equal to Kc. So this is an equilibrium. Okay? There's no shift of the equilibrium position. Now, think about what does it mean when QC is smaller than Kc. The ratio the last thought I heard is quite distinctive. Yeah, you do know when I'm talking about things that concepts that I think are important, I get totally serious. So I want you to think about this. The ratio of the initial products to the reactants is too small. Okay? The reaction quotient is smaller than Kc, which is the equilibrium constant. So to reach equilibrium, you basically need to make more products. Okay? So, to make more products, the forward reaction must be favored. You get this? Therefore, you shift the position to the right. Alright? Okay, so basically, as you make more products, QC should increase and therefore it will continue to increase until you reach equilibrium. Okay? Now, what if you have the opposite, another situation where QC is larger than Kc? That means the ratio of products to reactants is too big. Hey, one thing I want you to realize about for equilibrium reactions, you can start in a way, what you think of products and reactants is a bit arbitrary. I can start with what you call all the products, and I keep it in a flask. What will happen, right, is slowly the backward reactions will occur, and you start converting the products to your reactants until you reach the equilibrium. Okay, it's not a one-way process. That's why we have these situations. So the ratio of the initial products to the reactants is too big. To attain more equilibrium, you need to make more reactants. The backward reaction is going to be favored. So the position shifts to the left. Okay? And therefore, QC will decrease until you achieve equilibrium. Alright? Okay. One more slide just to summarize everything. Okay, so QC less than KC, it will shift until you reach the KC basically. Okay? Now, I won't go on to the next session, so I'll let you off. Yeah, let you off now.